we left off with chapter 9 and a discussion of hybridization. And let me make a slideshow here. There we go. Let's see. We left off with discussing the limitations of the localized electron model. And next I wanted to get into a discussion of the molecular orbital model. So you recall that the valence bond theory and the localized electron model treat molecules, and now we are talking about covalently bound molecules rather than ionic type compounds. So the localized electron model considers each atom as an independent player, and they only cooperate by overlapping orbitals, and that's how bonds form. But that didn't answer some very essential questions for describing how molecules are put together and how they behave, and frankly, energy levels for the electrons within the model, within the molecule. Let's see, Kathy's here. So the molecular orbital model is going to make an attempt, and succeeds fairly well, to answer some of these questions that the localized electron model could not. The molecular orbital model treats the molecule as a single unit. And once the molecule forms, all the electrons contributed by each individual atom become part of the molecule. It's like the the molecular equivalent to communism, right? The molecule now owns everything. And we construct orbitals at different energy levels within the molecule. We have a new set of orbitals. In fact, a new set of solutions to the quantum mechanical model that's applied to the whole molecule now, rather than to individual atoms. And these orbitals can be viewed as extending over the entire molecule. Which, when you come to think about it, we know that when you spread electron probabilities out over a larger area, you get more stability. So this makes sense to me. If we make those orbitals part of the whole molecule, then that tends to spread them out. That tends to stabilize the molecule. Now, it doesn't change reality, right? The molecule's here under one theory, and it's here under a different theory, and it's the same molecule. Right? We just have a different way of describing it with the molecular orbital model. Just a word about the term orbital. Orbital doesn't mean anymore. Orbital doesn't mean planetary model, right? The original Bohr model for the atom treated electrons as little planets that orbited the nucleus. And we've sort of grandfathered that term in, but it doesn't mean what Bohr originally thought it meant. But we still call them orbitals anyway. Okay, here's a comparison of the localized electron model and the molecular orbital model. The localized electron model relies on atomic orbitals to form bonds, whereas the molecular orbital model creates a whole new set of orbitals that belong to the whole molecule now. The quantum mechanical solution to the individual atom and its orbitals, those are extended into the molecule under the localized electron model. Whereas the quantum mechanical solutions to these equations, and these wave equations actually, are applied to the entire molecule now under this MO model. And this has been obvious from the beginning. The electrons are assumed to be localized for each atom. Come on in, join the party. Whereas the electrons now, under the molecular orbital model, are assumed to be localized across the entire molecule. I should say delocalized. Delocalization of electron probabilities, or we might say electron density, that diffuseness stabilizes the unit. We still have only 2 electrons per orbital. So when we draw an electronic structure for one atom, like let's keep it simple, say carbon, like that. Carbon would be like this, like that, and each one of these s orbitals has 2 electrons, and then there are 3 possibilities for p, and we have like that. But we still can only have 2 electrons per orbital. That hasn't changed. The energies under either situation are still quantized. In other words, when an electron is promoted to a higher molecular orbital, we have to add energy to get it there. It has to be just the right amount of energy to get it from one orbital to the next higher one, or to a higher one. Just as it was with the localized electron model, so it is with a molecular orbital model. All right, so when we put a molecule together and we form these molecular orbitals, we conserve them. In other words, how many orbitals are contributed from the individual atoms, right? In this case, we would have an S, one S, a 2S, and 2 2Ps, right? So if we combine that with, say, I don't know, oxygen, right, which would have 8 here, yeah. So now we would have 2, 4, 5, 6, 7, 8. Now, if this were carbon monoxide, then we would have 1, 2, 3, 4, and we could include this one. 1, 2, 3, 4, 5. And we had 10. We would have 10 molecular orbitals that we could construct. Now, they wouldn't all have electrons necessarily, but we would blend these into a set of molecular orbitals, and there would be, if 10 go in, atomic orbitals go in, 10 molecular orbitals come out. The way we do that is that if we put these 2 orbitals together, we get 2 types of molecular orbitals. One molecular orbital, say we had, well, let's move over here. Let's use these 2. We would build a molecular orbital that would have, we'd need 2 of them, right? If we counted those 2 atomic orbitals, we need 2 molecular orbitals. And what we do is we form one at a lower energy and one at a higher energy. And this one would be a bonding orbital. This one would be anti-bonding orbital. Okay? That's how we conserve the orbitals. Okay, we're gonna talk about why we need to do this. This is not just something that we pulled out of thin air, right? It's based upon those quantum mechanical equations and what's necessary to conserve all the orbitals and produce the desired results in our model that mimics reality. Okay, if we have two atoms, let's make it simple now. Let's say we have two hydrogen atoms. Right? They've each got an electron, one electron each, and they only have access to 1s and 1s from each one. Then we would have a bonding orbital that tends to concentrate its probabilities between the two atoms. And then we have anti-bonding, which tends to concentrate its electron densities outside. And there would be no probability in the anti-bonding orbital for electrons in between them. Okay, we're going to use this same terminology we did with the localized electron model. Sigma molecular orbitals are single bonds on axis with the two atoms that are bonded. Now, if it's between here, and this would be a sigma, then the anti-bondings would be sigma star. That's the terminology we use. Once the molecule forms, atomic orbitals no longer exist. They are history. They're gone. No more. The only thing that a molecule can have in this model is the molecular orbitals. So once we've created the molecular orbitals, the atomic orbitals are gone.
Waves can overlap. When that happens, the highs and the lows can build upon each other. Or they can align in such a way that they balance each other out. When they build upon each other, this is called constructive interference. When they balance each other out, this is called destructive interference. Let's look at what happens step by step when two waves travel through each other. Here's a moment when two highs overlap. This results in a combined high that's much higher. This is constructive interference. Now, here's a moment where all the highs are perfectly overlapping all the lows. We see a cancellation of the wave amplitudes. This is a moment of destructive interference. If you took a snapshot photo, you might think that nothing is happening. Change that to a video, and you'd see otherwise. In the next moment, you've got a case where the two lows are now overlapping. This results in a combined low that's much lower. Once again, we have constructive interference. So, constructive and destructive interference never occur at the same time. Instead, they alternate, one after the other. And then the two waves continue on their merry way, having traveled right through each other, amazingly unaltered. Check this out. A wave can bounce off of a rigid structure. Let's add a second wave. Cool. Let's add a second wall and try to confine a single wave. Aha. What we've got here is called a standing wave. Notice that to have a standing wave, the dimensions have to be just right, typically some multiple of the wave's wavelength. A musical instrument, such as a guitar or a flute, is engineered just right to accommodate standing waves, vibrating within the instrument, producing beautiful sounds. That's good energy.
Okay, so the concept we have here is that now and it's always been the same with both the localized electron model and the molecular orbital model. Electrons are treated as waves. So those Schrodinger equations that were proposed in the quantum mechanical model of the atom are solutions to wave equations. So electrons are treated as waves. So when we do that, we can treat them like any other wave with this possibility for constructive or destructive interference. Now, when a wave is, when two waves are overlapping each other, like they did in that video where they passed supposedly right through each other, once they meet and they start to interact, we call that superposition. And the result of that interaction is called interference. It can either be constructive interference or destructive interference, or actually anything in between, because those waves don't move over here and stand still and then move out here and stand still. I mean, they're constantly moving. So interference is either all constructive, all destructive, or somewhere in between. But I don't want you to get the idea that that means that we have an infinite variability in the atom, because the atoms are quantized. In other words, it's either it's either all constructive or all destructive to keep the electrons at these various energy levels. So in that respect, they don't strictly follow the wave nature, because they do have a quantized character. Okay, we're discussing constructive and destructive interference to try to get a handle on what we mean by bonding orbitals and anti-bonding orbitals. Here's a representation of the hydrogen atom. Right? It only has the 1s orbital available. When we combine those two, we can either get anti-bonding orbitals in the top example or bonding orbitals in the bottom example. Notice we have two orbitals going in and we have two orbitals coming out. Two atomic orbitals go in and one anti-bonding, one bonding orbital come out. So we've conserved orbitals. And that position between these two probabilities here is called a node. It's a node because there's zero probability of finding electrons there at all. The bonding molecular orbital here, I think we've used, the CHEM101 here is represented as the bonding orbital. And the CHEM102 is represented as the anti-bonding. What I would do, though, is I'd leave that one like it is, and I'd put a star on this one. That shows the anti-bonding. Now, what we know about the energies, actually the energies are reversed from where I drew them. Let me do it this way. Let me put anti on top and bonding on the bottom. Yeah. Then if we draw them in terms of energy, then the bonding orbitals, and these are the atomic orbitals that go in. Say we have a 1s here and a 1s here from the other hydrogen. When we create the bonding orbital, it's at a lower energy than the atomic orbitals, and the anti-bonding is at a higher energy level. So that means the bonding orbital is more stable than the atomic orbitals, whereas the anti-bonding orbital is less stable because it's at an elevated energy level. This also speaks to the positive benefits from molecular orbital theory is that now we can start to say something about energy levels. And in fact, the equations can be solved for absolute values for energy levels. We're not going to do that. I mean, it's the math is just too complicated, but it can be done. And you can say this orbital is going to have that energy, this one's going to have that energy. We can put numbers on them. Whereas with the localized electron model, we couldn't say anything about absolute values for energies. This is another way of drawing the construction of molecular orbitals from atomic orbitals. And we try to keep it really simple in the beginning by energy increasing that way, by putting the atomic orbitals that are going to be used on either side, and then the molecular orbital in between. So the atomic orbitals are here and here, and this one is a 1s with a 1 electron in it, and this one's a 1s with a 1 electron. So this is a hydrogen atom here, this is a hydrogen atom here. And each one has an electron in it. Okay, so we put in dotted tie lines. At lower energy now, we're going to have this bonding orbital down here, and it's going to be a sigma bond because that's the first one that forms. You always have a sigma bond before you have pi's. So we're going to have a sigma bond down here derived from the 1s orbitals. And then we're going to have an anti-bonding sigma derived from the 1s orbitals. Okay. Notice also that we still obey the atomic electronic configuration rules that we learned earlier. In other words, the Aufbau principle says that electrons go in at the next lowest energy level. As we add more electrons, they have to fill the very lowest possible energy level as we build up. So both of these electrons go into this lowest energy level, and we have room for two. But now one is upspin and the other one's downspin. So this is going to be the H2 molecule. And this is the molecular orbitals there. That's the very simplest example. That and probably mathematically the simplest to solve. This is just it's probably obvious that with this new model, the electron distributions and energies agree with our basic ideas of bonding. The lower the energy, the more stable. So we're likely to get a bond as long as we've lowered the energy here. So remember that diagram where we had we had energy here, and this was distance between the atoms, and we had energy on this scale. And we had the separate hydrogen atoms here. We had two hydrogens, and they were coming in, and as they got closer, their energy dropped to a minimum. And then it went back up like that. So this is where we have a bond formed. Here, lower energy. We have agreement with reality. That's what I'm always looking for when I see a new theory. Does it agree with reality? In this case, it does very well. The symbols and the labels that we give the molecular orbitals give us some idea as to the symmetry or the shape of the molecular orbital, and they're derived from the parent atomic orbitals. So we can see where this one originated. This sigma bond came from two 1s's, right? And they're symmetrical. And that's where we're going to start with homoatomic molecules, just two of the same type of atom. It's easier to visualize the molecular orbitals when they're both the same. It becomes a little more difficult when you've got, say, I don't know, oxygen on one side and nitrogen on the other. Right. We're going to look at one of those, but it's easier to start with homoatomics. So there we have the sigma 1s, right, derived from the 1s parent atomic orbitals. And that sigma means that they're on axis. And then the sigma star means it's still on axis, but the electron probabilities are outside. They're not between the molecules. And that's a trend that we observe with other bonds too. Okay. Let's see. Those are just statements of the obvious. How about difluorine? Has 18 electrons. So if we were to draw, remember we had a shorthand way of writing electronic configurations. I did one of those earlier for oxygen, where we had or carbon, where we had 1s2, 2s2, 2p2. This is for carbon. Well, you can do the same thing for molecular orbitals. And you start from left to right, lower energy, successively higher energy. Right? And then you can put 2 electrons into an s orbital, and we draw the pi orbitals derived from the p's. Actually, some of the sigmas can be derived from the p's. We'll have to draw you some examples. But the idea behind this simplified notation is that the energy increases from left to right, and we know how many electrons are possible, how many that we can put into each one. So we'll have to draw some examples to show you why you can only put 2 in the sigmas drawn from the 2s, or 2 go into sigmas and you can have 2 pi's. So we'll have an example in a moment. Before we get there, though, there's this concept of bond order. So what do we mean by bond order? Bond order is a way of calculating the strength of a bond in the molecular orbital universe. And the way we do it is, once we've drawn the molecular orbital and populated it with our electrons, we can count up the number of electrons in bonding orbitals. And that goes into here, the number of bonding electrons. Let's see. Yeah. Bonding electrons. And then we subtract the number of anti-bonding electrons and divide by 2. That gives us an idea of bond order. Now, it's not a one-to-one relationship, but bond order, if it's a whole number, it usually indicates whether the bond is single, double, or triple. Right? If it's a whole number 1, it's probably a single bond. If it's a whole number 2 bond order, it's probably a double bond. If it's a whole number 3, it's probably a triple bond. But we can still get fractionals in between. And the larger the number, the higher the number, the stronger the bond. If you get a bond order of 0, that's telling you that there's probably not a bond formed. For this example, where we have 2 here, we have 2 bonding, 0 anti-bonding, divide by 2, and that's equal to 1. So we have a single bond between the 2 hydrogen atoms. That's no great revelation, but it's just an illustration of the calculation and its intuition. What we normally consider a bond order of 1 would be a single bond. Right? So what if we have H2 minus? Right? If we add an electron to this one, right, it doesn't matter which one it came from, but we have the same structure here. But now where does that extra electron go? It can't go here. It has to go into the anti-bonding orbital, correct? So if we put it in the anti-bonding orbital, then we got one there. That means our bond order is 1/2. So we have decreased the bond order of this molecule by adding an electron to it. And we've weakened it because there's a relative strength, right? Half is less than 1. So we've weakened that bond by adding an electron. Oh, okay. Let's see. Yeah, let's go ahead and watch this one.
Today we're going to discuss molecular orbitals. But before we can get to molecular orbitals, we have to first consider atomic orbitals, something that hopefully we're all pretty familiar with. So let's start with hydrogen. Here I have 2 isolated hydrogen atoms. And we know that each isolated hydrogen atom should have 1 electron located in the 1s subshell when in its ground state. And of course, we know that these electrons don't move in perfect circles around the nucleus as I've depicted them here, but they do define a region of space defined by a sphere. But when 2 atomic orbitals combine to help form a chemical bond, something special happens. In the case of hydrogens, those 2 1s subshells combine and form a region of space known as a sigma molecular orbital. And a sigma molecular orbital is a region of space where the electrons live generally in between the 2 hydrogen nuclei, screening the repulsive force that their positive charges have on one another. So they stabilize, keeping these 2 nuclei close together. This is a bonding molecular orbital. But there's one rule that we haven't yet considered, and that is that the number of atomic orbitals going into an MO system must be equal to the number of molecular orbitals that that MO system contains. So our molecular orbital system is not yet complete in this depiction. We have 1 more molecular orbital that forms. That new molecular orbital that forms is called a sigma star molecular orbital. And it looks quite different from the sigma MO, doesn't it? If there were electrons inside of this sigma star molecular orbital, they would spend most of their time outside of the 2 nuclei, not screening their positive charge repulsions, and therefore would actually make the system very, very unstable. So let's think about what that means in terms of how hydrogen atoms come together to form a bond. In order to fully understand the molecular orbitals of an H2 molecule, we have to plot them in terms of energy. So here in this depiction, I've shown the 2 atomic orbitals here as these lines in blue. That will be our non-bonding energy. Unless there's an energetic benefit to forming molecular orbitals, these 2 atoms aren't going to get together and do that. So bonding molecular orbitals will be lower in energy, and antibonding orbitals will be higher in energy than this purple line that I've drawn. So let's combine these 2 different atomic orbitals into molecular orbitals and see what happens. When this happens, we always get a combination that is sort of centric around that non-bonding energy. In this case, we formed 2 new molecular orbitals from our 2 atomic orbitals. One is the sigma, one is the sigma star. Next, we have to populate our new molecular orbital system with the electrons that we know the atoms are bringing to the party. In this case, 1 from each. When we do this, notice that those electrons go into a lower energy orbital overall, and this lowers the overall energy of the entire system. So this energetic benefit that comes from forming and populating molecular orbitals leads us to the prediction that hydrogen will form a bond to another hydrogen. But beyond that, we can actually calculate exactly how many bonds will form. We call this the bond order, and it's calculated quite simply, using the number of bonding electrons minus the number of antibonding electrons, divided, of course, by 2, because we know it takes 2 electrons to form a chemical bond. In our example here of hydrogen, we have 2 bonding electrons and we have no antibonding electrons. Consequently, our equation tells us that we expect two hydrogen atoms to get together and form a chemical bond with an order of 1. In other words, a hydrogen molecule should have a single bond. And that is, in fact, exactly what we see. Now let's move on to the next element on the periodic table, helium. Now I've put molecular orbitals here in quotations because, as we're about to discover, there really is no such thing as a helium-2 molecule. But to prove it, we need to use our energy diagram and combine the two atomic orbitals of helium atoms to find out what the energetics of bonding would be if it were to happen. So let's go ahead and do that now. We combine them into a system with a sigma and sigma star molecular orbital, and then we populate that system. Now, in this case, I have two electrons that can fill the sigma bonding molecular orbital, lowering the overall energy. But I still have two more electrons that have to go into this new molecular orbital system. And they have no choice but to go up in energy and populate the sigma star. The consequence of this is that there's no real energetic benefit to bonding, so two helium atoms have no real incentive to get together and form an He2 molecule. And in fact, that's exactly what we see. When we calculate the bond order, we find that 2 bonding electrons and 2 antibonding electrons leads to a situation where we predict a bond order of 0. In other words, we don't predict a bond at all. And when we study helium in the laboratory, that's exactly what we find. Helium exists as isolated atoms. Now let's expand our discussion and consider the molecular orbitals of elements from the second row of the periodic table. We're going to begin with fluorine. Now, fluorine, we know, has available p orbitals because it's in the second row of the periodic table. So atoms of fluorine have 3 different 2p orbitals to donate to forming new chemical bonds. And within those orbitals, we know each has 5 electrons. So let's think about, first, how those atomic orbitals combine, and second, how those electrons can populate the new system energetically to make something that's beneficial. When we combine p orbitals, we find that we have a system that looks a bit different, don't we? In this case, a grand total of 6 atomic orbitals must combine to form a grand total of 6 molecular orbitals. Now, the lowest and highest in energy of these correspond to the in-phase and out-of-phase overlap directly along the nuclear axis. Those we would call the sigma and sigma star molecular orbitals. But we have some new players here. Those are the orbitals that result from the side-to-side overlap of p orbitals that we call pi and pi star MOs. So we have to figure out exactly where the electrons will go in this system and whether or not there's a real energetic benefit to putting them there, and that will help us determine whether or not fluorine will make a bond. Let's do that now. When we put all of our bonding electrons in, we notice that 6 total electrons go into bonding molecular orbitals. This is a tremendous energetic benefit. The sigma and the pi bonding MOs are completely filled. But fluorine has extra electrons, and they have to go somewhere. And the next best available option is to place them into the pi star molecular orbitals. These are antibonding, so the energy comes back up somewhat. However, notice that overall, we still have a system in which, on average, our electrons are in lower energy locations when they're in the molecular orbital system. There's a little bit of an energetic benefit here. And our calculation for bond order lets us know that when you have a grand total of 6 bonding electrons and a total of 4 antibonding electrons, you would expect that species to form a single bond. And in fact, when we study fluorine in the laboratory, that's exactly what we find. A molecule with a single bond. Now let's move on to something a little bit more complicated. Here's another second row element, nitrogen. Nitrogen also has 2p atomic orbitals available, but in this case only 3 electrons in each. So let's combine those and form a new molecular orbital system. You might notice something changed here, right? Notice that the sigma molecular orbital is actually higher in energy than the pi. And this is an interesting phenomenon. It's caused by something called sigma pi mixing. And we won't go into great detail into it here, but I wanted to point it out because this is how you'll probably see it in your textbooks. Nonetheless, when we use the electrons from nitrogen's 2p orbitals to populate this new MO system, notice that they all go into bonding MOs. And better than that, there's nothing left. There are no extra electrons to fill in those antibonding MOs and counterbalance the energetic benefits. So this is a tremendously energetically beneficial arrangement. When we calculate the bond order of an N2 molecule, we find that having 6 bonding electrons and absolutely no antibonding electrons, we expect a nitrogen molecule to have a triple bond. This is a very strong bond, which makes nitrogen gas almost completely inert. And again, when we go into the lab and study nitrogen, that's exactly what we see. A diatomic molecule with a triple bond. Now let's consider one more element from the second row of the periodic table. This time we'll consider oxygen. And I promise, I'm not wasting your time here. We're going to see something new. Now, just like any other second row element, oxygens have available 2p subshells. And we know from their electron configurations that each oxygen contains 4 electrons in those 2p subshells. So let's combine them to form some molecular orbitals. When we do this, we don't see any real surprises here. Sigma, sigma star, pi, and pi star molecular orbitals form. 6 atomic orbitals in, 6 molecular orbitals out. And if we fill them from the lowest energy to the highest, we notice that 6 of these electrons will go into bonding molecular orbitals, giving us a nice energetic benefit. But there are still 2 remaining electrons. And here's our new question. They clearly should go to the pi star MO, but should both electrons go into one, or should they each take a separate molecular orbital for themselves? The answer to the question is rooted in Hund's rule and the Pauli exclusion principle. Electrons will try to spread out and maximize spin. So, when they populate this new molecular orbital, they do so like this, raising the overall energy a little bit, right? Not enough to completely counteract all of those bonding electrons, so there will be a bond formed here. O2 molecules do exist. But even more importantly than that possibly is this. Notice that there are unpaired electrons in this molecule. And that means that our new oxygen molecule is paramagnetic. Liquid oxygen can be trapped within the confines of a powerful magnet. You may have seen this demonstration done before. And of course, just as before, our prediction is correct. If we calculate the total bond order of oxygen using 6 bonding electrons and 2 antibonding electrons, we find that the 6 and the 2 leads us to a calculated bond order of 2. Oxygen exists as a diatomic molecule with a double bond. So I hope that by now you're beginning to appreciate the power of molecular orbital theory. It not only confirms so many of the other topics we've already discussed on bonding, but it allows us to explain completely new properties that all of our other theories couldn't, things like the paramagnetism of oxygen. This is just the beginning of molecular orbital theory. You may want to consider in the future things like molecules that consist of 2 atoms that are not the same, or molecules that consist of even more than 2 atoms. There's much, much more to explore. But for this lecture, we're done. Thanks for watching, everybody.
Okay, so there's a lot of information there. Some of it we'd already talked about. One thing you may have noticed is when the molecular orbitals were being drawn, and we're only using the top level molecular orbitals. They weren't even using some of all of the valence orbitals, right? Because 2p's, you know, you've got 2 s's in there also. But when you calculate the bond order, it doesn't matter, because the pairing below those top levels are going to subtract out anyway. So calculating the bond order didn't matter. it wasn't sensitive to the loss of those lower molecular orbitals, but they do exist.
Today we're going to discuss.
No, we're not. Let's see. I had another thought. The okay, we're going to get to it. All right, so we're learning how to draw molecular orbitals. There was a mention of how the sigma and pi orbitals swap places. And we'll talk about that in more detail in just a few minutes. They call it sigma pi mixing. Sometimes you'll see sp mixing, but keep that in reserve for just a few minutes. So a homonuclear diatomic molecule has the same, homo means the same, has the same nucleus on either side. So 2 oxygens, 2 hydrogens, 2 nitrogens, 2 fluorines in the video were examples of homonuclear molecules, homonuclear diatomic molecules. And in that case, we can limit our discussion to the valence orbitals only. All right, when there was a mention there of paramagnetism. Paramagnetism is an observed phenomenon with all elements. We're going to focus our attention here on 2 of them, oxygen and nitrogen. Oxygen is paramagnetic, which means that it is attracted into a magnetic field. And it's attracted into that magnetic field because it has, remember those 2, let's see, sigma, those 2 pi, I think it was pi star. We had 1 here and 1 here. Those 2 electrons are not paired. Remember, when you pair electrons, you get a cancellation, so to speak. So when they're separate like that, they generate their own magnetic fields. And those induced magnetic fields will cause oxygen to be drawn into a strong magnetic field, an external field. That's paramagnetism. Para means alongside or with. So the oxygen is with the magnetism. Right? When we saw the nitrogen had the nitrogen had its sigma and pi's were all occupied. And the sigma star had nothing. I mean, the pi star and the sigma star had none in there. So that's why we had 6 minus 0 divided by 2 is 3, triple bond. All these electrons are paired. And that means that nitrogen will not be attracted into a magnetic field. It'll be repelled by the magnetic field. And that's called diamagnetism. So I got a picture, I think on the next slide. Well, here's how you measure it. Actually, you can measure the whether or not it's paramagnetic or diamagnetic with a very sensitive balance, and you lower your sample into a magnetic field of absolutely controlled strength. And you can either feel it being tugged into the magnetic field or repelled by the magnetic field, and that will register in the balance. So this is a measurable quantity. Here's oxygen being dropped into a very, very strong horseshoe magnet. Liquid oxygen, we use liquid oxygen because it's more likely to hold together. And notice it sits right there in the magnetic field. And it's going to be there until it absorbs enough energy to evaporate, in which case it's no longer susceptible to the magnetic field. That's paramagnetism. Now, I'm not sure I want to, yeah, I guess we will. We'll let Professor Dave talk.
It's Professor Dave. Let's revisit molecular orbital theory.
He knows a lot about the science stuff. Professor Dave explains.
We've learned a bit about molecular orbital theory and the ways in which it differs from valence bond theory. But let's expand on this knowledge now so that we can understand a phenomenon called sp mixing. But before we get into that, let's take some time to review the basics. First, let's compare valence bond theory and molecular orbital theory. Valence bond theory considers covalent bonds as being localized between a pair of atoms, resulting from the overlap of atomic orbitals or hybrid atomic orbitals. This overlap results in sigma or pi bonds, and we can use this theory to predict molecular shape. However, there are simple molecules that do not conform to this theory, like the diatomic oxygen molecule. Given this Lewis structure, where each oxygen atom has a full octet, we would expect oxygen to be diamagnetic and weakly repel a magnetic field. However, it does in fact exhibit paramagnetism, as liquid oxygen is attracted to a magnetic field. To explain this, we have to turn to molecular orbital theory, which differs from valence bond theory in that electrons are considered delocalized throughout the molecule, and atomic orbitals combine to form molecular orbitals, which are also delocalized throughout the molecule. These can be sigma and pi bonding orbitals, or sigma star and pi star anti-bonding orbitals. This theory ends up being better equipped to predict the arrangement of electrons in a molecule in certain situations. This is due to a process called the linear combination of atomic orbitals. In the modern physics course, we talked a little bit about the wave function, and molecular orbitals are combinations of atomic orbital wave functions. Just the way the wave function describes the behavior of an electron within an atom, molecular orbitals describe the behavior of an electron within a molecule. And just like atomic orbitals, they are filled when they contain two electrons of opposite spin. This theory requires that we strongly consider the wave nature of the electron. In the classical physics series, we talked a lot about waves and interference patterns. So to get the full picture of wave behavior in order to better understand molecular orbitals, check out this tutorial now. Otherwise, we simply need to understand that when two atomic orbital wave functions are combined, like these two s orbitals, there can be constructive interference, where the peaks line up with the other peaks. This causes the amplitude to increase, which results in a bonding molecular orbital, like the sigma s orbital. Most of the electron density is between the nuclei, which strengthens the bond. There can also be destructive interference, where the peaks line up with troughs. This causes the amplitude to drop to zero, resulting in an anti-bonding orbital, like this sigma s star orbital. Here, there is a node between the nuclei, which weakens the bond. The bonding orbital is of lower energy and will thus be filled before the anti-bonding orbital. For this to make more sense, we simply need to understand that these images of waves are just two-dimensional analogies to help us visualize the type of overlap. Electrons are three-dimensional objects, so the waves are in 3 dimensions, and constructive interference thus results in regions of greater electron density, while destructive interference results in regions of no electron density, which are depicted by these bonding and anti-bonding orbitals. We can do the same thing with p orbitals, utilizing direct overlap, which will yield sigma px and sigma px star molecular orbitals, or lateral overlap, yielding pi and pi star molecular orbitals from the overlap of py and pz atomic orbitals. Orbital number is always conserved, which is why the linear combination of 2 atomic orbitals will always result in 2 molecular orbitals, one bonding and the other anti-bonding. We can depict these linear combinations with molecular orbital diagrams, as we have seen. The dashed lines show how the atomic orbitals on the sides combine to form the molecular orbitals in the middle, such as we see here for hydrogen, with two 1s orbitals combining to form one sigma s orbital and one sigma s star orbital. If we go up to the electrons in the n equals 2 shell, we can see the 2s orbitals combining in precisely the same way, and then the 2p orbitals combining as follows, with the sigma bonding orbital and then pi bonding orbitals, followed by the corresponding anti-bonding orbitals. The good news is that these orbitals are still filled according to the Aufbau principle and Hund's rule, like we already know. This means that we fill them from lower energy to higher, according to Aufbau, and we will put one electron in each orbital for a set of degenerate orbitals before doubling them up, according to Hund. We've already learned in a previous tutorial how to fill in these MO diagrams for certain diatomic molecules, like O2, and how to use them to calculate bond order. Here's that diagram one more time, along with the calculation for bond order, with 10 bonding electrons, including the sigma 1s bonding electrons, and 6 anti-bonding electrons, including the sigma 1s star anti-bonding electrons. 10 minus 6 is 4, and 4 over 2 is 2. This explains the double bond in diatomic oxygen. But we also get an explanation for the paramagnetism of the oxygen molecule. We have two unpaired electrons in these antibonding orbitals, which does predict paramagnetism for this molecule. This is an example of the success of molecular orbital theory, as no other theory can account for this behavior. Now that we are up to speed, let's go over one other thing. The molecular orbitals that result from the combination of the 2p orbitals exhibit this order in O2, but this will change for other homonuclear diatomic molecules. Let's look at this diagram, which depicts the relevant orbital energies for all the potential homonuclear diatomic molecules in the second period, from lithium to neon. As we go to the right in the period, effective nuclear charge increases, so the atomic radii contract, and the orbitals get lower in energy. On the left, the pi 2p bonding orbitals are lower in energy than the sigma 2p bonding orbital, but on the right, the sigma 2p bonding orbital dips below and thus will be filled first. This discrepancy is due to a phenomenon called sp mixing, which influences the energies of these molecular orbitals. This happens when the sigma s and sigma p wave functions combine in such a way that the sigma s orbital becomes more stable and the sigma p orbital becomes less stable. As a result, we see the sigma s and sigma s star orbitals going lower in energy and the sigma p and sigma p star going up in energy. So much so that the sigma p orbital now sits above the pi p orbitals. Molecules like O2 and F2 have negligible sp mixing because the 2p orbitals in those atoms have some paired electrons. This raises the energy of the 2p orbitals, making them too dissimilar to the energy of the 2s orbital to allow mixing to occur. But going to the left on the period, where p orbitals have unpaired electrons or are vacant, the 2p and 2s orbitals are of similar enough energies that sp mixing will be prevalent and the order of the molecular orbitals will switch. While this is an interesting phenomenon, if we are only using these diagrams to calculate bond order, it won't matter because it is just the order of bonding orbitals that is being rearranged, so it won't affect a bond order calculation. Nevertheless, we have hopefully reached a more sophisticated understanding of molecular orbitals. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
So this, at first glance, this might be confusing until we draw the energy diagram for an example that has no mixing and one that has mixing. But the easiest way to know which is which, and for our purposes, we're not going to go into the third period. We're going to stay in the second period. It's easier to deal with. Notice that the breaking line between the mixing and non-mixing is between nitrogen and oxygen. So the oxygen, fluorine, and, well, dineon would be irrelevant because we know it's not going to form. It has a bond order of 0. So oxygen and fluorine are going to have no mixing. That makes the sigma bond, the sigma 2p bond, lower than the pi. So you have sigma bonding, pi bonding, 2 of those, and then the pi star and the sigma star. Whereas with mixing, once you go left of oxygen and get to nitrogen, now you've got pi bonding lower energy than sigma. So that's the observed and the useful difference there. It occurs between nitrogen and oxygen. Okay, here's another way of representing them. No mixing for oxygen and fluorine, and sp mixing for boron, carbon, and nitrogen. And notice that in this diagram, we've called attention to magnetism. So this diboron is paramagnetic because it has those unpaired electrons, whereas carbon and nitrogen have no unpaired electrons. They're diamagnetic. Oxygen has these unpaired electrons. It's paramagnetic. And fluorine has no unpaired, so it's diamagnetic. And we also have a calculation of the bond orders for these homonuclear diatomic molecules. And we get a peak at dinitrogen, and we see that in the observed bond energies. Right? Only 290 for diboron, it goes up to 620 for carbon, and 940 for nitrogen. And it drops back down for oxygen and fluorine. So that's why nitrogen is often considered an almost inert. And that's why all the potato chip bags that you buy at the store, they're puffed out, right? Rather than, they used to put antioxidants in there with your material, with your food, and they would absorb oxygen and keep the fats from going rancid over time. But there was some controversy over the effect of those additives on the consumer's health. So they found a way to get rid of those. And now instead, they just, when they're packaging the chips, they flush out all the oxygen, fill it with nitrogen, and seal it. Now there's no oxygen in there to start with. And nitrogen's not reactive with anything unless it's that's not enzymatic. So there you get the inertness of nitrogen coming to the rescue. Let's see. Okay. So there we make a point. All you have to remember is when there's mixing, you switch the pi and the sigmas. Okay. All right. So here now we're being introduced to heteronuclear diatomic molecules. On the left we have carbon. On the right we have oxygen. And notice the atomic orbitals from the start. We're looking at only the valence orbitals, right? The 2. We're leaving the 1s out. So if we look at carbon there, its s and p orbitals are much higher than oxygen. And that makes sense, right? Because oxygen has 8 protons, carbon only has 6, and those extra protons are drawing those orbitals in closer. They're lower energy. But when they overlap to make our molecular orbitals, we get notice that the lowest energy is this sigma formed from the 2 s's, right? So it's going to be lower than both this 2s and this 2s. And then the sigma pi's are going to be lower than both of the pi's. And remember, I don't know if you caught this, but when you look at a pi orbital on an x, y, and z coordinate system, you get x's like this, you get y's like that, and you get p's like this, right? Into and out of the board. So remember, sigma bonds are only formed on axis. So when you get two p orbitals coming together, you get these. These are the only ones that can overlap on axis. Right? So that's why when you've got p orbitals, you can get one sigma out of them. And the other two left over have to be off-axis interactions, which means that you can get one sigma and a maximum of two pi's out of the molecular orbitals out of those p's. That's why we have two lines there, or two positions for the pi's and only one for the sigmas. Okay. So once we drew those, then we populate them with the electrons that are given to us from carbon and oxygen, and they go in Aufbau principle, lowest energy to high. And Hund's rule, you only pair them up once you've got unpaired electrons in every degenerate orbital, then you can go back and pair them up. Okay, HF is a little bit different because hydrogen only has the one s. It's got to overlap with a 2p to form its molecular orbitals. All right, so we're going to have a sigma orbital that's much lower than the 2p of the fluorine and a sigma star that's higher than the 1s. And once we populate that, we find that we have a bond order of 1. Right? 2 minus 0 divided by 2 is 1. This diagram predicted that the HF molecule should be stable, right? And our calculation gives us a bond order of 1. Does it have its relative energy is lowered relative to free hydrogen and fluorine atoms, which is the driving force for a bond to form. The lower energy of the molecule versus the energies of the individual reactants favors a reaction. That hasn't changed with this theory. Right, so there's an artist's rendition. We still find, though, even with the sigma orbital populated with electrons, the probability shifts toward the fluorine, and that's due to its electronegativity. Okay. Right. The electron pair is not shared equally. And we find that the bond is polarized. Okay. We have this other problem with the valence bond theory and the localized electron model. And we talked about it before. It had to do with resonance, right? The solution to the problem then was resonance when we had two or more valid Lewis structures and we couldn't decide which, so we resonated them. Well, with the molecular orbital model, now you can say this is the orbital structure of the molecule. We don't have to deal with that resonance fix. But we're going to have, this is a combination. Yeah. This is going to be something of a combination idea. So that we can delocalize electron density and stabilize a molecule. And the next picture should show what I'm trying to talk about. All right, so here's an example of benzene. And benzene can be drawn with as a Lewis structure like this. Right? And then you've got hydrogens here, 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 here. Right? Each one of these has hydrogens. And in organic chemistry, when two lines come together, that's a carbon atom. So we don't have to draw so many carbons, right? Each one of those is a carbon. But we can also draw that same structure like this and move the double bonds around just one position, and we still have our hydrogens. And under the old model, under the valence bond theory and the localized electron model, we have to resonate those two. In fact, sometimes you'll see benzene or those with benzene rings in them drawn like that. Just as a simple way of getting around having to draw both of them. But this also has an implication for the idea of delocalization. If we go back to the valence bond theory, and we show the benzene molecules overlapping sp2 hybrid orbitals, then we know that each one of these carbons has an unused p orbital. And those unused p orbitals will overlap. And they will overlap in such a way that you get a continuous prediction of electron density above and below the ring. That delocalization stabilizes the benzene ring, and that's what this circle represents. This is known as a conjugated system. Actually, it's an advanced conjugated system called aromatic. Anytime you have a carbon chain, and we draw them like this, however many you need, alternating double bonds gives you a delocalized electron density over the whole thing that stabilizes those molecules as well. But once you get them in a ring like this, under certain circumstances, you get this aromatic system, and it's even stronger. Which this delocalization stabilizes the system. That's sort of a hybrid understanding of the molecular orbital model and the valence bond theory. This is what the nitrate molecule would look like with its three possible structures. And I mentioned this one earlier, where we drew in the dotted lines, because each one of these bonds, nitrogen to oxygen, are exactly the same strength, exactly the same length. So this would be the way I would like to draw it. But this is what it would look like with a delocalized pi bonding structure. Now we're showing you these things in terms of the localized electron model, but the molecular orbital model takes all of this into account. And if we drew the NO3 minus molecule energy diagram, we would find that those electrons in the pi bonding series would fit where they're supposed to with the pi orbitals. But that's a little four atoms in a molecule, even for me, is a stretch. Okay, one last thing. Yeah, we're a few minutes over. This analytical technique called the photoelectron spectroscopy. What it does is it determines the relative energies of electrons in individual atoms and molecules. So we can do this with atoms, we can do this with molecules, and what we direct at the molecule is high energy photons. So those photons will deliver their energy to the electrons, and then however much energy is required to eject the uppermost electrons, then remember we had this is the energy of a photon, Planck's constant times the frequency. That amount of energy is delivered to an electron in an outer orbital, and a certain amount of energy is required to eject it. That's called the work function. So much energy is required to eject it. This is the energy of the photon. So any extra energy, right? If we take the energy of the photon and subtract the energy of the work function to get that electron loose, then what's left over is kinetic energy of the electron. And that kinetic energy can be measured. And by doing this, by comparing that energy to this energy, we know how much we can draw a picture of sequentially ejecting electrons. We can draw a picture of the structure of either the atom or the molecule and draw this energy diagram. And here's an example. I'm not sure what's this coming from. It doesn't say. Anyway, so the whole point of this discussion is we can measure the energies of these various levels in the molecular orbital depiction of the molecule. Then we can calculate those energies using those equations, and they agree perfectly, the measured and the theory. So the idea here is that this photoelectron spectroscopy allows us to compare reality with the model, and they agree perfectly. Okay, that's it. So next week we're off Thanksgiving, and we'll come back that following Tuesday and do a review on this material. And then we'll have an exam on that Thursday. And then the week after that is review week. Okay, and no more labs. Just work on your labs and turn them in when you get back.